Dr. Nigel Winspear. Nigel is the head of Natural Catastrophe Analytics Research at Sompo International. Let me introduce him properly. Dr. Winspear is head of Natural Catastrophe Analytics Research at Sompo International, based in London. With over 20 years of catastrophe management experience, Nigel has worked with model vendors, insurers, brokers, and reinsurers across London, European, and Asia-Pacific markets. Originally a geologist, his PhD examined climate change impacts in the US over the past few thousand years and found evidence in Nebraska and California of dramatic, entirely naturally driven climatic shifts as recent as only a few hundred years ago, prior to the industrial era. That's an interesting theme for a PhD thesis. And I'm sure Nigel's presentation is going to be interesting and worthwhile too. Ladies and gentlemen, please join me in welcoming Dr. Nigel Winspear. Over to you, Nigel.
Thank you, Andreas. Good morning from London. Good afternoon to you all in Singapore. I'm just going to share my screen now. You should have my screen now. Good.
Yes, we can see your screen now.
Okay. So my talk is entitled, as you can read, as it's all to do with modeling climate-related catastrophe or cat risk. It's going to be fairly high level. I'm going to cover quite a bit of ground. I've got 10 slides of real content, and I've got about 35 minutes or so. So just over 3 minutes per slide. Let me just launch into the agenda. I'm going to be talking about global climate in terms of how we think it's likely to change in future and the basis for how we know this. Basically it's climate models. Climate models have very definite limits, which has been publicized fairly recently. Those limits are pretty poorly known or understood outside of climate modeling world. Regulatory timelines, we'll see that there's some mismatches with the capabilities of climate models versus the regulatory expectations. And of course, if we're then looking to transmit that information into projecting catastrophe risk into the future, we need to make sure we're bearing those limitations in mind as well. Fortunately, there are some studies available. This is point 6. So I'm going to just cover a fairly recent paper on tropical cyclones that is commensurate or appropriate for use in the future for projections. And this, of course, will be of interest to anyone who's looking at typhoon risk in East Asia. Number 7 is implementation. How would we go about implementing those? There's 2 real camps as to how we implement those in a cat risk model. And then just a quick brief synopsis at the end as to what we should do next. Right, so on to the first of these. Now, you're probably aware, because everyone here has an interest in sustainability. So in 2015, at the Conference of the Parties 21, so UN body, most of the United Nations, 195 nations, adopted the Paris Agreement or Paris Accord. And the point of that, or the agreement of that, was to hold global mean surface temperature to below 2 degrees above pre-industrial levels. Pre-industrial is typically measured 1850 to 1900. Okay, and then there was a secondary subsidiary goal, which is as far as possible, if it really is possible, can we all get together and try to limit the rise to 1.5 degrees C, if possible. So how does this stack up in terms of what's actually happened? Well, if we look at the chart to the right, so the x-axis is time from 1900 up to 2100, and the y-axis shows the global, it's actually the global mean surface temperature or the change in the warming. Okay, so 1900 is really the end of the pre-industrial era. The black line up to 2005 shows the historic change in global mean surface temperature. You can see that it has actually increased, as you would expect. And then from 2005 onwards, we have these projections. And these projections are represented by what's known as a IPCC representative concentration pathways, or RCPs. You can view each of these. The mean is the solid line in each case. You can view each of these as a climate change signal under different greenhouse gas emissions pathways. Each RCP has a number attached to it. So RCP 2.6, for example, that 2.6 is measured in watts per square meter, and it's measured at the top of the atmosphere. So in other words, if we follow that emissions trajectory into the future, which is quite ambitious, and I think is fairly unachievable, we can realistically expect the emissions to lead to an increase of 2.6 watts per square meter measured at the top of the atmosphere. So the crucial point here is we don't really know how this is going to play out in future. Obviously, it's really quite an uncertain series of projections. We can say that RCP 8.5 is probably unachievable now, because there have been significant steps by the major economic blocs in the world to implement climate adaptation, greenhouse gas emission reduction strategies. RCP 8.5 assumes almost no action, no mitigation activity whatsoever. So RCP 8.5 is extremely pessimistic in my view, and RCP 2.6 is extremely optimistic. And in fact, a lot of the literature tends to concur that RCP 6.0 is more likely. But as you'll see, up to about 2070 there, it's actually quite difficult to resolve RCP 6 and RCP 4.5 on a mean basis from each other. There's also a significant cone of uncertainty around each of those RCP climate change signals, and they are overlapping heavily. And they overlap heavily, especially between 2020 and 2050, which is really our time frame of interest, right? So it's really difficult to say which one we're following necessarily at this point. Now, you may at this point ask, where are we? So I've plotted 1.5 degrees, which is this ambitious Paris Accord target. Globally, we're not there yet. We haven't on an annual basis, but on a monthly basis, there have been cases where that 1.5 degrees limit has been breached. We're not there yet. For 2 degrees, that is likely to take another couple of decades or so under most of those RCPs. Now, the takeaway from this slide is it's very difficult for climate models to resolve the RCPs from one another. And it's also very difficult for climate models to resolve RCPs from natural climate variability on anything less than several decades or 20-year timescale. And as you can already see, between 2020 and 2050, there's such heavy blur. It's actually very difficult for climate models to actually to resolve RCP pathways across the world. This is really important, right? Because these are presented as mean annual signals, whereas actually the catastrophe perils we're interested in, they tend to work on a seasonal basis. And of course, what actually matters is the degree, for example, of warming in those particular months. If you have warming in winter months and not in summer months, then the peril itself will be significantly less adjusted, less impacted. So anyway, but the takeaway from this slide is that there's heavy blur in terms of projections, and that climate models really do struggle to resolve RCPs anything less than about 20-year timescales. Basis for knowing this, this is all based on climate models. Climate models, there are two main types. General circulation models. Now these are the global scale atmospheric and oceanographic models. They're coupled together, ocean and atmosphere, and they can because they're run at a relatively coarse resolution, they can be projected over many decades into the future. We have the computing capability to do this. Right, so the GCMs in particular are capable of representing large scale, or as we say, synoptic scale, 1,000 kilometer scale features, atmospheric gyres, oceanographic gyres, and different circulation features. So they're good at doing that, and they have skill in doing that, and they can project it into the future. And these really are the basis for the IPCC projections. Now, it's also possible to have a higher resolution type of model known as a regional climate model. This can be run on its own, or it can be embedded and fed or forced by a general circulation model. And the diagram to the right shows, the black area shows a regional climate model embedded within the global climate model. Okay, so that's known as downscaling or dynamical downscaling in this case. Stepping back, GCMs, they use a very coarse horizontal grid. So we're looking at somewhere between 50 to 100 kilometers and several tens of kilometers in the vertical dimension as well. That resolution, whilst you can represent, you can identify large scale perils, and I'm looking at larger hurricanes and extratropical cyclones. These are the type of European windstorm events, which are hundreds of kilometers across. You can't really look at the detail of such events using GCMs, which is why you would then use an RCM, a regional climate model. These have higher resolution, 10 to 30 kilometer horizontal grid resolution. And of course, that enables you to pick out more detail, to simulate more detail of larger scale hurricanes and ETCs, extratropical cyclones. Within an RCM, it's also possible to dynamically downscale by embedding a very high resolution numerical weather prediction, NWP model within an RCM, and have it forced by the RCM. So it takes the inputs, it takes the outputs of the RCM as inputs into the NWP model. These typically have grid resolutions of 1 to 10 kilometers scale. So, and in fact, the lower right-hand box there shows an NWP model applied to a hurricane, to the lifespan of a hurricane. You can pick out the structure of a detail of a hurricane in the Gulf of Mexico there. For the most intense hurricanes or tropical cyclones, category 5, these can be just 10 kilometers across, right? So if you're using a 10-kilometer grid, you can't resolve detail of that. You need an even finer detailed grid. And the same applies for many much smaller scale extreme events. So I'm thinking of convective storms, particularly tornadoes, small wildfires, which do comprise the majority of wildfires, localized flash flooding from extreme precipitation events, all of which are sub-kilometer scale, none of which can be explicitly represented even in an NWP model. Like these require very, very fine scale grids and very high frequency of refresh of a model in terms of time steps. It's just, today we would struggle very much to do that, let alone projecting that into the future. Stepping back up to even the NWPs, when you're modeling a hurricane lifespan, you can't project. You can run that for the lifespan of a storm, but you can't project it even to 2030, let alone 2100. So of course, our confidence in projections of such perils into the future is low. Our confidence with projections of larger scale atmospheric perils, larger hurricanes and extratropical cyclones is much higher as a result of this. So limits on our predictive capabilities, on our skill. There's an excellent paper in Nature published in 2021 by Fiedler et al. And I'll point everyone to that really in the end. And it really does summarize the limitations of climate models. And one of the takeaways is that these are not really widely known outside the climate modeling community. So it's good to raise it here. The first of which is time horizons. We've touched on this already. Natural climate variability, swamps for climate change signal as represented by the RCP means, at projection leads of less than several decades. Right, so that means for any projection that you would see that's a 5 or 10-year projection lead is unlikely to be robust, even for these larger scale perils. Geographic scales, also, even RCMs, they're suitable for use at subcontinental scale to global scale. Subcontinental, obviously you're looking at the scale of India. In an ocean basin, that might be the tropical North Atlantic or the tropical part of the West North Pacific, or at a push for South China Sea. Right? Anything smaller than this, I'm thinking of southern China, Vietnam, Malaysia. These are much smaller scales, right? Any out of the box projection is going to be not robust for such geographic scales. We would need to downscale the projections, either using dynamic downscaling, which is the modeling, by nesting higher resolution models, or by statistical downscaling, which is based on historic associations, or by empiric relationships between variables. And of course, that's uncertain, and that uncertainty increases as we project into the future, right? So ideally, we would look at projections which are 20 years plus in duration and which apply at a subcontinental scale plus. When we think about extreme or catastrophe events, I've already mentioned that in terms of limitations, yes, the models can represent them, but they can't really pick out the detail very well. You'd have to go down to an NWP model to do that. And because, and if you don't go down to an NWP model, for category 5 hurricanes or tropical cyclones, which may be 10 kilometers across in terms of radius to maximum wind, you may not be able to resolve them. So of course we could be understating potentially. So basically the only models that can be projected for decades out in terms of lead are the regional climate models and the general circulation models. You can't predict an NWP model 20 or 30 years into the future due to computational limitations. So that means that if we're relying on RCMs and GCMs to tell us about hurricane frequency, we may potentially be understating the frequency of the strongest storms, category 5 storms. And then the second limitation is that these very, very small scale perils, convective storms, majority of wildfires, extreme precipitation events, as we say, we struggle today, even today, to represent those properly in NWP models, which are the finest models available, let alone in the future, right? So, those projections are likely to be not robust. Okay, so this slide should be of quite some interest to a room full of actuaries. How do regulatory timescales compare with these climate model limitations, right? So, well, just to start off, I've listed 4 significant regulators and 1 task force there. All of them, apart from 1, has a long-term stress test type timescale, and that long-term horizon is compatible with the capabilities of climate models to project robustly into the future. Okay, it's only in that case, it's only the US Fed, but I'm not aware of a long-term projection in that case. It's clear that regulators, and probably justly so, they're of interest in much shorter time frames, which are of relevance to businesses and to industries. So 5 to 10 years, for example. But that time scale is well within. It's less than the capability of climate models to resolve the different RCPs. We need at least several decades for that. They have skill several decades on. This basically means at these short and medium term risk horizons, there is a mismatch between what regulators would expect in terms of financial disclosures and the capabilities of climate model projections. right? So obviously, this raises the possibility of misstatement of risk in climate-related financial disclosures over these shorter time frames. Right? And that was raised quite well by Fiedler et al. Now, I'm inferring this, but to me, it's fairly straightforward. But, if you are misstating your risk, then potentially some of the potential outcomes from that, it could be the holding of inappropriate levels of capital, or the taking of inappropriate mitigation or adaptation activities that could affect your underwriting or investment decisions. I won't go any further into that, but I would point everyone in this room to Fiedler et al. At that point. Now, the focus of this talk is on catastrophe risk modeling. I'm aware this is a room full of actuaries, so most, if not all, will be aware of what a catastrophe model is. But for those who don't, a catastrophe model is a way of simulating the whole range or ensemble of possible events that could potentially happen over a very long time frame, but actually could happen in the current year at a range of different probabilities. So you could have, in the current year, you could have very short return period or high frequency events, or very long return period or low frequency events at a much lower probability. Okay, so CAT models are there to actually provide that scientifically based or engineering based view. Uptake of CAT models had a step change in the wake of Hurricane Andrew in 1992, image to the right, and again after the Northridge earthquake in 1994 as well. CAT models are used. These really are, in terms of acute physical catastrophe risk, when we're making those disclosures to regulators, CAT models are the basis for making those. Calculating expected loss and PML, probable maximum loss, at a snapshot in time, which is usually today, to a portfolio. So these are portfolio analysis tools from a wide range of extreme events. Crucially, CAT models are intended to represent a long-term climatology. So that's a historic climatology. Out of the box, they are not suited for use at future points in time. So as if it were 2030 or as if it were 2050, we can't use current catastrophe models without adjustment. So we need to adjust for frequencies and severities of the stochastic event set in order to represent these future climates. And of course, just a bit circular here, these frequency and severity projections as to how the frequency and severity of stochastic events are likely to change by 2030 or 2050. For example, they're based on climate model simulations, which, as we have seen, have very clear limitations. So when we're looking to make adjustments, we should be using what I would describe as robust projections, which focus on risk horizons of several decades ahead and which work at subcontinental scale and above. Fortunately, and I'll show this in the next slide, such data does exist for large-scale perils, hurricane in particular. But before I do that, I just want to tackle one question, which is, or one argument, one criticism, which is routinely leveled at CAT models. And this is one I often raise myself, is that we're not confident today of the most extreme event rates I'm looking at, so 1 in 100, the 100-year event or beyond. So how then can we project them into the future with any confidence? And that's a very good question, and I would say that yes, it's absolutely right. But for higher frequency events, we have much better handle on their occurrence rate. But certainly for the upper tail loss events, 1 in 100 and beyond, I agree, we're not confident of their rates today, and that's because of very small or absent sample sizes. And I'm thinking about, for example, 1938's New England hurricane or the Long Island Express that made landfall on Long Island in New York in 1938. Major hurricane, Category 3 status. There's only been one since records began in 1895. Right, so is is its historic frequency is about 1 in roughly 140 years or so. What's its actual return period, its likely return period? We don't know. There's only been one. There could easily have been none, right? So very small sample sizes ranging from 0 to 2 typically over a very long period of time. It's extremely uncertain today what the rate is. If we then look to project that into the future, of course, there's going to be a severe degree of uncertainty in terms of that projection. Major hurricanes cause a majority of loss, right? Especially in such populated areas. Yeah. Right, so just stepping back, this is an example, it's a widely cited example of the sort of adjustments that have been proposed under future climate states. Now, this was made by Knudsen et al. In 2020. It's a widely cited paper, as I said, and it's basically the basis for adjusting hurricane models in particular. I've seen this used by other major model vendors. In short, Knudsen et al., they looked at over 100 climate model tropical cyclone studies, and they have divided them by parameters. So by that I mean in terms of event frequency, sustained wind speed, precipitation rate. And they've classified them by ocean basin and by storm intensity category. So that's Saffir-Simpson hurricane wind scale, category 0 to 5, where 0 is a tropical storm, category 5 is the strongest hurricane or typhoon, and category 3 to 5, which are the major hurricanes, which are the strongest storms. Crucially, this is measured over a 2-degree increase in global warming. So from that potentially rather confusing text, you can pick out the fact that 2 degrees C, if you wind back to the first chart that I showed you, that's looking at potentially several decades into the future. Ocean basin scale is subcontinental scale and above, right? So big thumbs up for this. This does work. It's, the climate model projections on which these parameter projections are based are likely to be robust. They have skill when working at these levels. So as an example, the top chart shows globally and by ocean basin how we think tropical cyclone frequencies for category 0 to 5, that's all of them, are going to change. So it's box and whiskers. You can see a very wide range. There's an interquantile range specified by the grey box, and the flat line inside the grey box is the median. So if you look at the medians, it's fairly clear that we're expecting, on average, a slight reduction in the frequency of tropical cyclones into the future with 2-degree global warming, which sounds a bit intuitive, counterintuitive. Right? We're going to get less of these storms. However, what's actually is going to happen is that we're expecting them to increase in severity. Okay, so we're expecting an increase in the proportion of the most strong storms, category 4 to 5. This is the lower chart. Okay, if you look at the median there, the y-axis scale is quite different as well. On average, we're looking at quite a significant increase in the median frequency of strongest storms. So overall, we're looking at a reduction in the overall rate, but an increase in the frequency or proportion of the strongest part of those, which can only be balanced by a reduction in the proportion of the weakest storms as well. So we're expecting category 0 to 2 to decrease and for category 4 to 5 to increase. Right, so and you can actually look at a particular basin. So I'm talking to the Singapore Actuarial Society, so the Northwest Pacific and potentially the Indian Ocean will be of greatest interest in. So you can pull out parameter values for how we think that frequencies are going to change, and there's similar charts for sustained wind speed and for precipitation rate as well. And those, so the actual figures on which these charts are based are not presented in Knudsen et al., but they are used in a study by Steve Jewson in 2021, who's actually pointed out that actually it's quite difficult to apply the Knudsen projections as is to a cat risk model. And the reason being is that there is no clear starting point for the 2-degree increase in global warming that Knudsen et al. Specify. They implicitly assume that these changes will happen no matter when you start. Whereas Steve Jewson provides good arguments and also freely available downloadable code in R that you can use to adjust these parameters to match the historic catalog from which the cat model was based. So in the case of vendor cat models, they tend to, for hurricane, certainly in the North Atlantic basin, they tend to be about 1900 to 2018 to 2020, that sort of time frame. Right, so in which case, into the code, Jewson's code would then rebase the projection parameters here in terms of frequency. You can do this for intensity and precipitation rate as well. And then the resulting parameters will be consistent with the time frame from which the cat model is designed to represent. This is really quite important because I'm thinking of in the Northwest Pacific, so some of the data sets for hurricanes, for tropical cyclones in particular, may be starting in 1955, for example. So that's really quite different from 1900. So in which case you'd want to make sure your 2-degree warming rebased to 1955 is done appropriately, and these parameter projections are rebased appropriately. So I would point everyone in the room to Steve Jewson's paper in 2021. These papers are listed at the back of this report. Just looking at my watch, we're mindful of time. I'm going to move on very quickly into how would we implement such adjustments. The first option of which is the most commonly done DIY, do it yourself, right? And therefore, naturally, it's the most common way. We're looking at making adjustments to the frequencies and/or the severities of the stochastic events in the cat model stochastic catalog. Of course, that could shift the loss distribution and may change its shape as well. Crucially, this method uses loss as a proxy for hazard, right? And that's really a gross simplifying assumption. Obviously, loss is not linearly related to hazard, right? So loss isn't a direct linear function of wind speed. However, what else are we to do? As model licensees, we only have loss results from the model. We don't have direct access to the hazard model. In the ideal world, what we'd be able to do is the hazard model would be open and we'd be able to adjust the frequencies of the actual events and then let the model catalog play through and produce the impact on losses. We can't do that. We just have the losses available. Right? So as a result of this, these sort of projections, they tend to be quite conservative, especially when used for stress testing or other regulatory disclosures. How would we go about implementing such changes? It's always via post-processing for model results applied to the losses, as I just said, and it very much depends on the format of the cat model. So for event loss table based models, that's typically RMS. We would typically adjust the frequencies of the storms directly. In certain cases, you could even do this in Excel, right? You just calculate, if you want to make a 20% increase to all category 4 hurricanes making landfall in the US, you just identify those which from the list, and then you just physically adjust them, right? And then you have to reproduce the EP statistics yourself. For year event loss table, YELT-based models, that's AIR of the risk, and the more recent RMS models, we need to do resimulation, right, which obviously requires a bit more skill to do this, to reproduce the desired changes in frequencies. If we're trying to reduce the overall rate of tropical cyclones, but increase the proportion of category 4 to 5s and decrease the proportion of 0 to 2s, we can do all of that. We just need to resimulate it, right? The last point of this slide is that we need to be careful if we're also looking at applying loss severity adjustments, for example, for increased intensity or precipitation rates in a warming atmosphere, we need to bear in mind that if we've already shifted the distribution towards stronger Cat 4 to 5 storms or towards weaker storms, then so certainly if we've shifted it towards stronger storms, then we risk double counting if we are then applying severity increases as well. Right, so we need to bear that in mind. The second option, less common at the present time, but it is my personal favored preference, is to license a climate condition stochastic catalog directly from the vendor. Right? And typically this will represent their view as to how catastrophe risk is in their model is going to change between now and then at a specified future horizon, which I believe usually one is able to specify. They've done all the rebasing of the parameter projections themselves, and there is typically for a given RCP. So you should be able to get a category for a catalog, a climate condition catalog for different RCPs. The advantages of this are obviously because it comes from the model vendor, so it's scientifically informed and justifiable. It's quickly available. You don't need to employ climate scientists on your staff. You may have to get a contractor, but you don't need to physically employ them, so you get a saving then. And the great advantage from my perspective is that, as I've pointed out, the changes are made to the hazard, not to the loss. And therefore, they represent robust, justifiable adjustments. And the changes to the hazard will ripple through the financial engine into the final losses. So they are commensurate or reflective of the adjusted hazard. They're not made up in terms of guesswork. So that's a great advantage. The con, of course, is the additional licensing cost per catalog. And then the one I've highlighted is the fact that, if you're just getting this from a model vendor, it's very easy to default to the vendor in terms of knowledge. Knowledge transfer from vendor to client can potentially be quite limited, especially if you haven't got your climate scientists on staff. Certainly, the more advanced regulators like model licensees to own their view of risk, and certainly not to import it just from a model vendor. As I pointed out, uptake of climate conditioned cat model catalogs is, I believe it's fairly limited to date in the market, but I suspect it may change in future. Right, my final slide, recommendations. What should we as a community do, in my view? The first of which, and we've covered this here, I think that we should all be familiar with the limitations of climate model outputs, aiming to use the model right. So in other words, that's starting at several decades projection lead at subcontinental scale and above. These limitations should be, ideally, embedded in regulatory frameworks to remove the obvious potentially contradictory element there. Third point, we as a group should be fully aware that cat risk analysis is an uncertain science. In fact, I'd probably even call it a pseudoscience, really, and especially when projected into the future. So, okay, granted all of that stuff. So we now still need to do this for regulatory purposes in particular. How do we do this? So I would point 4, we decide a robust future risk horizon, so 2050, so that's just under 30 years time, and seek projections, for example, Knudsen et al. For tropical cyclones, showing how these large-scale perils can change over large areas. Okay, we need to rebase those, typically using adjustments, for example, Steve Jewson's paper that I've pointed to ensure consistency of the historic catalogue. And then, of course, we need to decide and execute our implementation option, either DIY or license a climate conditioned catalog. And then finally, as with all things, this is continual professional development. We need to keep abreast of climate science because typically we have to repeat these steps with updates and improvements every year for regulatory climate risk reporting, right? So there are typically own risk self-assessments, ORSAs, for example, that need to be submitted every year, right? This information typically should go into that as well. So we need to be looking to make updates and improvements, which keeps us aware of the improvements in the climate science. Right, that's it. Thank you for listening. Andreas, back to you.
Yes. Thank you, Nigel. Thank you for this interesting and very insightful presentation. While we are waiting for the questions to come in, please type them into the Q&A box below. So while waiting for the questions, I've got 3 questions for you, Nigel. What benefit is there in projecting our current catastrophe risk 20 to 30 years into the future? Are there any reasons why we might want to do this or might want to avoid this?
Okay, so that's a very good question. This really does touch on the question that many people struggle with when asked by regulators. You know, what's your view of your risk in 2050, for example? And so, of course, you know, we go through these steps and we produce projections as to, you know, as if it were 2050, this would be our risk, and these are this is what it would mean in terms of capital available and reinsurance protection, etc., on a gross and net basis. But in reality, it will never be that case, because between then and now, between now and then, there is time on an annual basis to prune and adjust the portfolio, right? So if, for example, certain things become uninsurable, then we will have time to adjust. Okay, so now that sort of a adjustment mitigation capability isn't taken into account by these projection studies, these snapshot projections, right? So so it's to me it's still a bit uncertain as to why regulators would necessarily want to see what's see our risk as if it were 2050. And how would your current protections respond? Well, it's not 2050, and if it were, then we would have already adjusted the portfolio and the protections on an annual basis all the way up to 2050. Right? So we would have mitigated against that. Yeah.
Okay, thanks. I've got 2 more questions, and then 1 question has come in from the next speaker. So my question, what could cause, you know, on your slide number 10, the climate condition vendor CAT models, which is basically licensing an additional stochastic catalog. And the uptake hasn't been great so far. So what would cause, in your opinion, what would cause a widespread uptake of those climate conditions vendor CAT models?
Yeah, certainly from my side, 2 things. First of which would be supportive pricing from the CAT model vendors, right?
Right, yeah, as always, yes.
As always. And then the second point would be, so that's the carrot, and then the stick from the regulators. You know, if regulators encourage, if they demanded more detail, were more rigorous in terms of, you know, rather than just, I think most people just follow the DIY approach, right, which is adjusting loss, but, you know, that can be overly conservative. I would say that use of a climate condition CAT model could actually potentially provide a competitive advantage, right, in terms of regulatory disclosures at that point. Whether that's actually you know, implemented in practice and provides actual competitive advantage is a different matter. But certainly in terms of your regulatory disclosures, they could be less, presumably be less, if you're using a climate condition vendor model. Yeah. Right.
1 more question from me. I hope the question is not going to open a can of worms. Try to give a short answer. Are there any wider factors that are not considered by climate models? For example, changes in the sun's irradiance or major volcanic eruptions. We all know volcanoes can also drive the climate.
Mm-hmm. Yes, I think you've just touched on both of those actually. So longer scale changes in solar irradiance or insolation falling on the Earth's atmosphere, absolutely. These changes, longer scale changes, have been targeted as explanations for naturally driven climate change. Volcanic eruptions, major volcanic eruptions, these occur very infrequently. They do tend to last, 3, 5, 7 years in terms of their impact, cooling impact. So yeah, these are, and they're difficult to, so they're not really, neither of which are particularly included in climate models. And over decadal timescales, I think that's okay. Over projections to the 2100, we might want to include such factors. Yeah.
Right. Then last question. The question is coming from Joseph Wang Lu, who is also the next speaker. Adjusting frequencies and severities may have a funny outcome to simulated events around the location/footprint. For example, flood polygons that are deeper but appear as a cliff at the original edge of the polygon. How do you address this?
Well, firstly, you notice I haven't mentioned flooding in this, but yes, absolutely. If you're looking to make adjustments to flood models, now that is actually so. In the ideal case, when you're looking to adjust a flood model, you'd be looking first of all to adjust the rates and severities of the extreme precipitation events, and then of course you'd be looking for the hazard model to automatically let that ripple through into the actual footprint modeling. Right, so ideally the user wouldn't be making their own adjustments to the footprints, right? Because there's a disconnect at that point to the extreme precipitation rates that cause the flooding. Yeah.
All right. Thank you, Joseph, for the question and for your patience. Your slot will be coming up soon. And Nigel, thank you for the very insightful presentation and